Welcome to you all. So let's look at kx. We said that the plate wave number is kp. Okay. So let's say the plate was not vibrating, but now it vibrates. So there's a pulse on the plate like this, and therefore a point in the medium air got lifted up here. Okay, and then the wave moves towards the right. So the wave has moved like this to the right. Okay, and so another point got lifted up because the medium is connected, medium is contiguous to your vibrating structure, and then this point moves here, right? And then at the next instant, let's say the wave in the plate moves here, so another point got lifted here, whereas this point came down here and this point came down here. Okay, and therefore particles of air that were contiguous with my structure, they move along with the structure, and therefore we can say that my kx is bound to be equal to kp. Okay, kp is the plate wave number, it's known to us. So now kx is known to us. Okay, so what happens? I have now kz, the only unknown, okay, which is equal to k square minus kx square. Okay, and therefore kz is equal to plus minus square root of k square minus kx square. Okay, k square minus kx square, but kx is kp, so this is equal to plus minus square root of k square minus kp square. Okay, so let me write it here once more. Kz is equal to plus minus square root of k square minus kp square. Now the relationship between k and kp becomes important. If k is greater than kp, then I have a real quantity. Kz is a real quantity. Whereas if k happens to be less than kp, then kz will be an imaginary quantity. Imaginary quantity. Okay, so we will have to examine these two cases. Okay, and in addition we have to choose the sign, because there is a plus and minus. Okay, we have to choose the sign based on some physical considerations. Okay, physical considerations. So let's look at that. Okay, my kz is equal to plus or minus square root of k square minus kp square. Okay, and my sound wave solution px comma z comma t in the 2D half space was what? Some amplitude e to the power j omega t e to the power minus j k x x e to the power minus so this is also e to the power minus j k p x, and here minus j k z z. Okay, where now z has these possibilities. Z has these possibilities. Okay, so first let's see. if k is greater than kp, okay, then kz is a real number. Let the positive value be phi, okay, then it is going to be plus or minus phi, okay. Then the description, sound field description is b tilde e to the power of minus j k p x, I put it separately, e to the power j omega t plus or minus j phi z, okay, because kz became phi, plus or minus phi, so I will have plus or minus j phi z, okay. Here is the thing, the sound field on the plate is exciting what is happening in the z direction, okay. So this is a cause, okay, and this is the effect. So any sound field should look like it is moving in the positive z direction. It should not look like a sound wave is coming from infinity towards the plate, because it's not possible, there is no source at infinity, okay. So if you look at the z direction, it should appear that the sound field is moving from the plate towards infinity, okay. Now e to the power j omega t minus j phi z, this descriptor says that the sound field is moving towards infinity from the plate, okay. I will discuss this in the next class maybe, but here please take it, this minus sign, okay, indicates that the plate is generating the sound and the sound field is moving towards infinity, which is physically possible. Whereas the other descriptor, if I choose the other sign plus j phi z, okay, what this says is that there is a sound field which is coming from infinity towards the plate, okay, and there is no source at infinity. We are describing the problem, okay. So this is not possible. So when k happens to be greater than kp, we have to choose the positive sign for kz, then it becomes minus j kzz, okay. When we choose the positive sign for kz, it becomes minus j kzz, and then that descriptor works well with the causality, okay. On the other hand, the second case, when k happens to be less than kp, okay, kz is an imaginary number. So how does it look like? That is equal to plus minus I square root of kp square minus k square, okay. And therefore how does the pressure description look like? P x comma z comma t is equal to b tilde, again I will leave the x wave number separately, e to the power j omega t, okay. Now there's, so please note that I and j I use interchangeably, okay. So don't get confused, both mean the same, square root of minus 1. I've got used to both, okay. So I've used j somewhere and I somewhere, they are the same. So I have j omega t minus j kz. Kz is what? Again plus minus j square root of kp square minus k square into z. So if you examine this part, there are two j's coming in, right? So I have e to the power minus j, and I can choose a plus j or I can choose a minus j, and then a square root. That's a real number now because I have switched kp with k, kp greater than k, and then a z. Okay, so this minus j into j gives me plus. If I choose it this way, if I choose this combination, a positive imaginary, okay, so j square is negative, I get a plus. I get a plus square root of some real number into z. Whereas if I choose the negative imaginary, then this negative goes with that negative, then j square gives me negative. I get a negative square root of kp square minus k square into z. Okay, so I have now two choices. What is it? I have e to the power j omega t, which is fine. I have either e to the power plus a real number into z, or e to the power minus a real number into z. Okay, so this e to the power j omega t and this which is there in the exponent, I am putting this out for the moment because it's there. Now this, as z goes to infinity, blows up. Okay, this description as z tends to infinity blows up, whereas this as z tends to infinity decays to 0. Okay, so in linear systems, for a finite amount of power that is given, I cannot have an infinite sound field at infinity. Okay, it is not possible. I cannot put so much power into the system without breaking or doing some damage. Okay, we have only finite energies. Mind you, infinity is bigger than any number you think. Okay, any number you think, infinity is bigger, so you cannot have large sound field there. Okay, so the only logical, physically plausible situation is a decaying sound field. So I need to choose the negative sign here, negative imaginary. So in this case I have to choose the positive when k greater than kp. Here I have to choose the negative when k less than kp. Okay, here there is a propagating sound field. This is a propagating sound field in the z direction. Why? It is of the form e to the power j omega t minus some real number z. It's a propagating sound field. Okay, so the e to the power j phi z is oscillatory, just as e to the power j omega t is oscillatory, e to the power j phi z is oscillatory. Okay, whereas here I have e to the power j omega t, but I have e to the power of minus some phi z or psi z, let's say. Minus psi z. So minus psi z decays with z. So the behavior is radically different. Whether k happens to be greater than kp or k happens to be less than kp, the behavior is radically different. Here there is a propagating sound field, propagating sound field. Here this is a decaying sound field. Okay, so it's a 0-1 situation. K greater than kp, you have propagating, k less than kp, you have decaying. Okay, so let us see now. k, the acoustic wave number we said was given by omega by c, which is equal to k, okay, and c is a constant. C is more or less constant with frequency. The speed of sound in air is more or less constant with frequency. So omega by c is k. So that means what? If I plot k as a function of frequency, it will be a straight line. It will be a straight line. Okay, this is my omega axis. This is my k axis. Okay, so that's the behavior for air. Now we said the 1D plate was given by d del 4 w by del x4 plus m dash mass per unit area del 2 w by del t square is equal to 0. This is the equation of motion. And we also said w was given by a e to the power of j omega t minus kpx. Okay. So if I substitute this back, what do I get? I get d, okay, fourth derivative of e to the power of minus jkp x. So I get jkp to the power fourth, okay, into a e to the power of j omega t minus kpx, then the time part plus m dash, two derivatives of time gives me j omega whole squared, and a e to the power of j omega t minus kpx, that is equal to 0. So this part is common, I can take it out. So I am left with the other. So j to the power fourth is 1. So I have d kp fourth, and j omega gives me a negative. So I get m dash omega squared. So kp, if I want, becomes omega to the half power, then fourth root of this quantity, m dash by d. So whereas k moved as a linear function of omega, kp moves as a kind of a parabola. So if I plot both on the same axis, okay, so this is my acoustic wave number, sorry, this is my acoustic wave number, okay, and this is my plate wave number. Acoustic wave number goes off, okay. So now what? There is a region where this is kp, this is k, this is k, this is kp. You see both the inequalities have come up, right? Here let's call this a certain omega c, okay. So below omega c I have k less than kp, and from earlier description, decaying sound field or no sound field, whereas greater than omega c, where k happens to be greater than kp, propagating sound field. Yes, there is sound. Okay. So that frequency, this frequency now is called the coincidence frequency. Coincidence, or some people call it critical frequency, where the acoustic wave number is equal to the plate wave number. Okay. So I said that the main idea in structural acoustics, let me just, the main idea in sound structure interaction this is the main idea. Sound fields, okay, are largely generated by thin structures, thin plates, okay, thin shells. Okay, that means what? The type of wave they carry is a flexural wave. Flexural wave. Okay, a transverse wave. Transverse wave. That means you have this sort of a behavior. Okay, the particles move this way, the particles of the plate move this way, whereas the wave moves that way. It's a transverse wave. Okay, that's how the medium can be compressed. This region is compressed, this region is rarefied, this region is compressed, this region is rarefied. So let me say plus for compressed, negative for rarefied. Okay. So flexural waves are the ones that generate sound fields. Okay, and flexural waves are efficiently present in thin plates and thin shells. Okay, so and a flexural wave has this dependence on frequency. The Kp is typically proportional to the square root of omega, whereas the acoustic wave is proportional directly to omega. So there is always a coincidence frequency. Okay, so such that below coincidence K happens to be less than Kp, and above coincidence K happens to be greater than Kp. Okay, so that here there is no sound, here there is yes sound. This is the central idea. This is a central idea in sound structure interaction. This decides many other issues. Okay, this decides many other issues. As opposed to a flexural wave, what wave could you have? You could have a longitudinal wave, the one I kind of showed you in a spring. You can have a longitudinal wave. So there is this bar or rod, and there is a longitudinal wave. Okay, there are regions of compression, the regions of rarefaction. Okay, but if there is a acoustic medium in the neighborhood, there is no efficient transmission of this longitudinal movement to air. Okay, the only way is if a flexural wave gets excited. That's when you have the neighboring medium being compressed and rarefied. So a flexural wave, a transverse wave, interacts with the sound medium in the neighborhood, and the flexural wave has this behavior, a square root omega relation. Okay, whereas the acoustic wave has an omega relation. So this always happens. This always happens, and this is crucial to sound structure interaction, and therefore the coincidence frequency is a very important idea in sound structure interaction. Okay. So let me close the lecture here for today. We'll continue with this the next class. Thank you.